Hello everyone. Today we are going to start behavior of gases. This is also known as gaseous state also we can call, because majorly in the matter we have a 5 states of matter we know. In that states of matter, first one is solid state, liquid state, gaseous state, plasma state and Bose-Einstein condensate state also we have. So out of that the gases we study, especially liquid state we will study, solid state we will study, like that only gaseous state of the molecules we will study separately. Solid state separate, liquid state separate and gaseous state is separate. So in that gaseous state we are going to study the behavior of gases. What is the behavior of gases? Nitrogen gas is there. How nitrogen gas it behaves, what are its physical properties, what are its chemical properties, what are the gaseous properties? And to explain these gas properties, we have some gas laws, Boyle's law, Charles' law, Avogadro's law. We have different types of laws for the explanation of this behavior of the gases. So in today's we are going to start behavior of gases, and today's video we are going to cover the topics physical properties of the gases. We are going to cover physical properties of the gases and measurable properties, means in which units we are measuring the gases, and also some gas laws. That too in today's video we are going to cover Boyle's law and Charles' law. Okay, Boyle's law and Charles' law. So let us start our today's class, right? Come. So first of all, the properties of the gases. First of all, physical properties of gases. So how to know what are these physical properties of the gases? We are studying from the lower classes that solids, liquids and gases. Because suppose if you take a chair is a solid, one glass of water is liquid, and perfume bottle, in our daily life what you are using, the perfume bottle, that is a gas. Cooking gas, cylinder, that is a gas, isn't it? At the house we are using for the domestic purpose, that is the gas we are using. So what are the, suppose one chair is there, you are keeping one chair at one place. Unless and until if you apply some force on that, that chair will not move itself from there. It will be there only. Somebody should come and should move this. Until then that will be there only. It cannot travel and it cannot move, because the particles present in that chair are strongly, forces of attraction between the particles are stronger, and there is no gap between that molecules present in the solids. It was we are studying from the lower classes, right? Even for liquids, the forces of attraction between the molecules is little bit far than this compared with the solids, and because of the less forces of attraction they will have some gaps between the molecules. That's why it has that's why the liquids does not have any particular shape, but they will take the shape of the container. They will take the shape of the container, right? So what about the gases then? Gases, there is no forces of attraction between the gases. It is very negligible, and the distance between the particles is more. Distance between the particles is more. That's why if you spray that bottle, then the gas molecules of that spray or that smell comes throughout the room. If you leak the gas, that gas smell will absorb in. If it is in one room, we are in another room, also we can absorb that smell, because the gas particles are spread, because the forces of attraction between the particles are negligible. This is one of the most property of the gases. In physical properties is considered, the forces of attraction between the molecules is very negligible, and the distance between the molecules is more, they spread over. Because of this nature, the gases will not have a particular shape, even they will take the shape of the container. If you fill that in the cylinder, it takes the cylinder shape. If you fill that in the 1 liter perfume bottle, it takes 1 liter bottle shape. If you take small, it takes a small. So because of this nature, it takes the shape of the container, right? So that is one of the very important property when compared with that. So they do not have any definite shape like solid. They take the shape of the container in which they are storing, in which we store that one, right? Gases do not have any specific volume, like gases occupy the entire volume available. If you give the space only this much, the gases will occupy only this much space. If you give this room space, the gases will occupy the complete room space. Okay, so they don't have a particular volume, like they take the volume how much it is possible to spread over, they will take that much volume. So we cannot fix the volume of the gas, right, when it is in a open container. And the molecule force of attraction between the molecules are negligible, and the distance between the molecules also more, and they will go to the different directions. They will undergo some random collisions. See, the gas molecules will move inside the room. What happens? They are moving like this. So there will be a collision between the glass, between the particle and the particle with the collide container or with the walls of the container. Everything there will be some collisions. That is what we will study as a collision theory also. Because of those collisions, the random collisions will be taken place, and also possess very little weight and low density. They are very less densifiable because they are spreading over. The particles are not at all to be nearer. That's why they are more low density, low melting and boiling points, and they have some exerts pressure. Gases exerts the pressure. How gases exerts the pressure? See here, if you are giving the space to occupy this room, then they will occupy completely this room. No, you are giving to them small container, they will occupy the small container with the same volume. That is nothing but they are under pressure. If you are increasing the pressure on the gases, the molecules in the gases will come nearer to each other and they occupy less volume. So gases exert pressure in all directions, not only one direction, right? So decrease in the volume of the some quantity, there will be some compressibility factor, and gases exhibits the expandability and diffusion, means the more diffusion. These are the general physical properties of the gases, right? Now what are some measurable properties of the gases? See, measurable properties is nothing but gases we can measure by through its pressure, through its volume, through its temperature, like that it has some measurable properties. The first one is volume of the gas. What is this volume of the gas? Volume of the gas is nothing but as gas particles occupies the entire free space available. How much space is available to them? The gas particles will take that much space and they will take this volume of the container in which it is stored. That one we measured in liters. The units measured that volume is in liters or in milliliters or dm cube or cubic centimeter, means cm cube. All these are the units of the volume. 1 cubic centimeter, and these are the conversions. 1 milliliter gives you 1 cubic centimeter. 1 liter means 1000 ml. We know that 10 cube milliliters. And 1 liter is the 1 cubic decimeter. 1 liter is 1 cubic decimeter. Right? So these are the conversions. Next we have a pressure. What are the measurable properties of the gases? First one is the measurable property of the gas is volume, and then pressure also, because by applying the pressure on the gas, the volume of the gas will be decreases. What is this pressure? First of all, pressure of the gas depends on the force exerted by the gas particles when they collide with each other. When you are applying some pressure on that, then the particles come nearer to each other. While they are coming nearer to each other, there will be a collision between the particles of the particles and the particles and the walls of the container. Then they exert some pressure, isn't it? So this pressure we can calculate per unit area of the container. Means if you are giving more volume, less pressure. Less volume, more pressure they will feel. If you see, balloon is there. In that balloon we are sending some air, bulging the balloon. Whatever the air present inside the balloon under pressure, what is the air present in the balloon under pressure? That is because so much of air we are keeping in a small area of the balloon. If you keep a small hole to that balloon, it makes a sound and it comes out. Why? Because whatever the air is present inside, that is coming from low pressure region to high pressure region to low pressure region. So the volume of the gas is same, but when it occupies the more volume, pressure is less. When it is occupying the low volume, pressure is high on that, right? So the pressure, generally the units of pressure is atmospheres, and we can calculate in torr bar also, atmospheres torr bar, and mm of Hg or centimeters of Hg, right, at the sea level. So, 1 atmosphere conversions, these are these conversions helps us to do the problems in behavior of gases which we use in the gas laws. So, these conversions also very important. 1 atmosphere is 76 centimeter of Hg or 760 mm of Hg. In centimeters if you take, that is 76, in millimeters if you take, that is 760, or even you can write 760 torr, 760 torr, 1 torr equal to 1 mm of Hg. Even in SI and CGS system, units of pressure is Newton per meter square. N is nothing but Newton per meter square. This is called Pascal. Newton per meter square is also called Pascal. Pressure can measure in pascals, and dyne centimeter square, dyne per centimeter square. These are the units which we use in the conversions while doing the applications in behavior of gases, right. The next one. So, whatever the pressure we have taken, to measure this pressure, 76 centimeter of Hg or 760 mm of Hg at the sea level, how to measure this pressure? To measure this pressure we use some device that is called barometer. See here, at any place atmospheric pressure is known with the barometer. So, the measurement the instrument which we use to measure the pressure at any case, that is called barometer. The atmospheric pressure is measured by barometer and the pressure of the gas is measured by manometer. So, here too, barometer, manometer. Barometer we use to pressure and the manometer we use to measure the pressure of that gas. Whatever the gas we are taking, to measure the pressure of that gas we use the manometer. So, a device used to measure exerted pressure by a gas is known as the manometer. How it will be? How will be the manometer and barometer? See here, this is the barometer we use, this is the glass tube and this is the vacuum inside, and it is the atmospheric pressure. By using this barometer and this mercury level, here we kept some mercury, the mercury, based on this mercury level, how thermometer, armpit thermometer is there, how much heat the mercury starts melting and it shows some temperature, that one will take as the body temperature, either fever is there or not, like that we are using. At the same time, here this mercury shows the level of the pressure. This is called barometer, and manometer will be like that. This manometer we use for the particular gas, to measure the pressure of particular gas. Gas will be taken here, and this is the gas and this is the mercury column, and height of the mercury column will gives the pressure of the gas. Means inside the container, under which pressure, means how much pressure this gas is present, gives by this manometer. Okay. And next one is temperature of a gas, which these are the very important factors while talking about the gases laws: volume, pressure and temperature. That's why we are discussing all the gas laws, Boyle's law, Charles' law, Avogadro's law, Hamilton's law. All these laws depends upon these pressure, volume and temperature conditions only, right. So, next one is temperature of a gas. First we finished volume of a gas, next pressure of a gas. Now this is the temperature of a gas. How to measure the temperature of a gas? We know is proportional to the average kinetic energy in the moving molecule. Means temperature is proportional to kinetic energy of the molecules. So, if you are applying more pressure, the particles are coming nearer, so they will move more. When the movement is more, that is directly proportional to the temperature. And the units of temperature we know, degrees Celsius or kelvins. 0 degrees Celsius, always degree Celsius is equal to 273 Kelvin. Whenever while doing the applications, the conversions, degree Celsius we have to convert into the kelvins. How to convert the Kelvin? Suppose here we have 1 degree Celsius, this one you want to convert into kelvins. Then what we have to do? 1 plus 273 gives you 274 kelvins, means 1 degree Celsius in kelvins is 274. These are the conversions, and we have a foreign heats also, but here we use only degree Celsius and converts. Whenever in the problem they given degree Celsius, you have to convert that into kelvins by using 273. Right. Now, what are the standard temperature and pressure conditions? Already while discussing the previous classes, we study with the STP conditions. This STP means standard temperature and pressure conditions. These are also known as normal temperature and pressure conditions, STP or NTP. Means at these STP conditions, the values for the pressure, temperature and volume will be fixed. What we have studied, that measurable properties, pressure, volume and temperature, these are the measurable properties of the gases. These measurable properties at constant values if they have, those are called STP conditions. Yet STP conditions always we have to take temperature, we have to take temperature is 0 degrees Celsius and pressure is 1 atmosphere temperature, 1 atmosphere pressure. This is also sometimes referred to as NTP. This NTP we also known as STP or NTP conditions. Always the volume will be 22.4 liters. At normal standard temperature, temperature is 273 Kelvin and pressure is 1 atmosphere, means 760 centimeter mm of Hg or 76 centimeters of Hg. So these are the normal, means standard temperature and pressure conditions, right. Now pressure, volume, temperature is completed, then what is the mass of a gas? Mass is nothing but how many number of atoms or how many number of molecules are present in the given gas, that gives its mass, measured as the number of molecules of the gas. How many number of molecules are present, that gives its mass obviously, right. Now come to the very important. Till now we have studied some introduction part, but in the behavior of gases, now we entered into gas laws, which is very important, right. So the first gas law is Boyle's law. What is the Boyle's law? We know this. Till now we have studied this Boyle's law. What is this Boyle's law actually? See, Boyle's law is nothing but at constant temperature, means at room temperature we can take, or at constant temperature, we kept the temperature constant. When you are increasing the pressure, then volume of the gas decreases. Suppose see here in this figure, you can observe in this figure, this is the container. In this container we kept some gas. The piston was here. Piston was here. They have some space, they occupied some space, and the distance between the molecules also more, right. So what I did, I pushed the piston down. I pushed the piston down. That one you can observe in the second figure. If the pushed the down, then the pressure on the molecules increases. You are giving the pressure, you are pushing, then the pressure increases and the space, means the distance between the molecules decreases. They have compressed to here half. Means if you are increasing the pressure, volume of the gas decreases at constant temperature. That is what Boyle's law. What is Boyle's law? At constant temperature, pressure is inversely proportional to volume. Inversely proportional is nothing but volume is inversely proportional to 1 by P, or P is inversely proportional to 1 by V. Anything we can write. Then I want to remove this proportionality constant and we keep K. Then V equal to K into 1 by P. Then it will be PV equal to K, which means constant. PV equal to constant. If it is a constant, we can write this formula. If you apply this formula for two different gases, then P1 V1 equal to P2 V2. This is the formula for Boyle's law. PV equal to constant means P1 V1 equal to P2 V2, where K is the constant, right. So P1 V1 equal to P2 V2. How to represent the graphical representation for Boyle's law? Boyle's law is very easy. At constant temperature, if you are applying some pressure, volume is decreases. Pressure increases, volume decreases. P is inversely proportional to V. PV equal to constant. If you take two different gases, then P1 V1 equal to P2 V2. Now the graphical representation. On one axis I have taken on one axis I have taken pressure, on another we have taken volume. Pressure is increasing, pressure value 1, 2, 3 like that, pressure is increasing, then volume will be decreases. That's why we are getting the graph like this, hyperbola. Means this is the PV, always the graphical representations are very important, because P value is increasing, then V value will be decreases. Now come to the PV. I have taken now graph for volume V and PV. Just before we have studied that PV equal to constant. If PV is constant means there is no change in the graph. If you are increasing the volume, no change in PV. PV will not increase, PV will not decrease. So we will observe the straight line like this. If you take PV here, suppose the graph you taken PV here and volume here you have taken, you are increasing, then the graph will be like this. Means line towards the PV. If you take PV on y axis, then line will be like this. If you take PV on x axis, then line will be like this. There is no change in PV because it is a constant. Now here it is 1 by V and P. P is inversely proportional to V but directly proportional to 1 by V. 1 by V means reciprocal to V, right? So P increases, 1 by V also increases. P increases, V decreases. You have to remember that difference between V and 1 by V. It is P proportional to 1 by V. 1 by V. P. P is directly proportional to 1 by V. P increases, 1 by V value also increases. P is inversely proportional to V. Means only this one we consider. P increases, then V decreases. P increases, 1 by V value also increases. This difference you must understand. Here the graph is given P and 1 by V. Both are directly proportional to each other, right? So P increases, 1 by V value also increases. Then P is increasing, 1 by V also increasing. Then you will get the graph like this, straight line from the origin. So these are the different graphical representations which are very important in examination point of view also. This is the Boyle's law and its graphical representations. Now come to the next one. So graphical representations are completed. So I want to explain one graph for one problem I want to explain for Boyle's law. So let us see the Boyle's law. What is the problem given here? Boyle's law. The pressure of a gas is 2 atmospheres at 5 liters. If its pressure is increased by 3 units, and then what will be its new volume? So in this question clearly we can understand the relation between the pressure and volume he is asking. What is the initial pressure they have given? Pressure is 2 atmosphere. Pressure is 2 atmospheres. Pressure is given 2 atmospheres. This one I am taking as P1 and yet 5 liters. Yet V1 volume is 5 liters. If its pressure is increased by 3 if its pressure is increased by 3 units, this is very important. He asked pressure is increased by 3 units. So first of all, P1 equals to 2 atmospheres, V1 equals to 5 liters. Then P2 is increased 3 times, not 3 times. P2 is increased 3 units. 3 units of P1 means 3 plus P1. 3 units he said, not 3 times. If it is 3 times, it will be 3 P1. But 3 units, so we have to take 3 plus P1. What is the P1 value here? 2 atmospheres. So it totally 5 atmospheres. So total it is 5 atmospheres. Now he is asking to calculate the volume. So what is that Boyle's law? We know the relation PV equals to constant, that is nothing but when two different conditions are taken, P1 V1 equals to P2 V2. P1 V1 equal to P2 V2. Then P1 is 2 atmospheres, V1 is 5 liters. Then P2 is 5 into V2. So anyway 5 will get cancelled, then V2 gives you 2 liters. So when 5 liters pressure is 2 atmospheres, when at 2 liters pressure is 3 units means 5 atmospheres. So this is the problem, this is the application for the Boyle's law, behavior of the gases in Boyle's law, and its applications we have completed. Let us see the next one, modified Boyle's law. Boyle's law means P1 V1 equal to P2 V2. Here we have a modified Boyle's law. What is that modified Boyle's law? Let us see. So the relation between pressure and density of a gas at constant temperature is as follows. Yes, volume means what? Mass equal to volume into density, isn't it? What is that we know? See, PV equal to constant, it is the normal Boyle's law. But in terms of volumes, if we consider PV equal to constant, P1 V1 equal to P2 V2, this is the normal Boyle's law. But whatever the volume we have, volume, what is the density? Mass into volume is called its density. Then I want volume, then mass by density if you substitute, then Pm by D equal to K. What is the relation here? Pm by D equals to K. But mass of the given one is constant, there is no change, and K is also constant. Then what we can write, it is Pm equal to Kd. K is constant, M is constant, so we can write it is P1 by D1 equals to P2 by D2 for two different conditions. P by D equal to K by M, which is constant. So we can write P1 by D1 equal to P2 by D2. This is called modified Boyle's law. When we substitute in place of volume, mass by density, right? This is also we can use in the problems. If he gives the density, then we have to use that, right? Comes to the next one. Next one is the Charles law. What is the Charles law? Boyle's law is the relation between pressure and volume, right, at constant temperature. Charles law is the relation between the volume and temperature at constant pressure. Okay, at the given constant pressure, volume means volume is directly proportional to temperature. This is the Charles law. First of all, who has proposed this one? This one given by Charles. Jacques Charles has generalized this Charles law. This is at constant pressure, volume is directly proportional to the temperature. Okay, then if you take only at the normal, then V proportional to T. Then if you remove the proportional and keep the proportionality constant, V equal to KT, right? Then V by T equal to K, which is constant. So this one we can write V1 by T1 equals to V2 by T2. This is the Charles law, right? V1 by T1 equal to V2 by T2. P1 V1 equal to P2 V2 is Boyle's law. So, but here he observed some difference in the temperature. That is nothing but at constant temperature, the volume of given mass of a gas is decreases or increases by 1 by 273 of its volume at 0 degrees Celsius temperature, which is called absolute zero temperature. Means minus 270, 0 degrees is nothing but 273 Kelvin at 1 by 273 of its volume. So, he has modified that Charles law, V proportional to T as Vt, means V at particular temperature equal to Vt, V0 means at 0 degrees Celsius plus V0 into 1 by 273 into its temperature. This is the observation he has taken. So, Vt equal to V0 into 1 plus T by 273. This is already we discussed that V equal to Kt, V is proportional to T here, right. So, let us see here. This is very important. Volume occupied by any gas at minus 273 degrees Celsius, which is called absolute zero temperature. So, then it is modified, means the Charles law we have been modified at minus 273 degrees Celsius is V minus, temperature has taken as minus 273, previous it is Vt equal to V0 into 1 plus T by 273. So, this Vt has taken as minus 273. Then in place of this also, if you substitute 273, this get cancelled and overall Vt, V volume at minus 273 is becoming 0. Because 273 get cancelled, then it is 1 minus 1 means 0. So, the overall value is 0. Then volume of a gas at minus 273 degrees Celsius is at 0. That is called absolute zero, right. So, it is defined as, how they have defined it is as the temperature at which no substance exists in the gaseous state. At absolute zero temperature, no substance is existing. At absolute zero temperature, no substance is existing with particular volume. That is called absolute zero. Right. So, here we have some conversions. 0 degrees means 273 Kelvin, 10 degrees means 283 Kelvin, but minus 273 means minus 273 plus 273 means 0 Kelvin. This is called absolute zero. At 0 Kelvin, that at 0 Kelvin temperature, there is no substance is existing at particular volume, right. So, this is called volume occupied of any gas at minus 273 will be 0. So, these are some graphical representations of Charles law. What is the Charles law? V by T equal to constant, right. V by T equals to constant. V by T equal to constant. If you take, so then V1 by T1 equal to V2 by T2. So, both are directly proportional. If you see here, on one axis volume, on another axis temperature, both are directly proportional to each other. So, the graph we can observe straight line passing through origin. If you take volume and it is Celsius scale, means degrees Celsius scale, if you take, we can observe this straight line not passing through origin and it is going to minus 273, absolute zero temperature, that is what, 0 Kelvin temperature, minus 273 degrees Celsius. At Celsius scale, graph is this. At absolute scale, graph is this. If you take V by T and T, see here, V by T is constant. If V by T is constant, is nothing but there is no change. That's why a straight line over the temperature. If you increase the temperature also, but there is no change in its V by T value because V by T is constant. So, these are the some graphical representations of the Charles law, right. Now, let us see one problem on Charles law. 5 liters of a gas means he given some volume. Let us see, volume I am taking as V1. V1 equal to 5 liters. 5 liters of gas is collected at 100 Kelvin, means T1 is given 100 Kelvin, and then allowed to expand to 20 liters, means V2 is given 20 liters. What is the new temperature in order to maintain the same pressure? Means at constant pressure, V1 is given, T1 is given, V2 is given, he is asking to calculate the T2. So, apply the formula V1 by T1 equal to V2 by T2. You want T2, then T2 equal to V2 T1 by V1. So, substitute those values in this. V2 20 into T1 100, no need to convert because in the problem they given directly kelvins, by V1 is 5, 5 4s are 20, so it is 400 Kelvin. So, what is the new temperature? 400 Kelvin. So, these are the applications of the Charles law, right. So, thank you. So, today in behavior of gases we have studied properties of gases, measurable properties of the gases, and gas laws, Boyle's law, Charles law and its graphical representations, and we have done with some applications how to do the problems on Boyle's law and Charles law. So, I hope you understand today's class, right. Thank you so much.